Hello, Dr. Harris here with uh, video slideshows for Chapter 8 in our Statistics Math 111 course. This time our topic is linear regression. So we're going to do a little bit introducing some of the ideas behind uh, regression analysis and learning some about how we would use RStudio to help us with some of these things as well. So in this video, we're going to be talking about the line of best fit. We'll be talking about correlation, and we'll also be talking about something called residuals. These things will all be hopefully clear to us by the time we're done with this slideshow/video. So what we're going to be doing in this chapter is looking at a pair of numerical variables. And if you go all the way back to our work in Chapter 1, one of the very first things we introduced through RStudio was a command called xyplot, and it generated what we call a scatter plot, basically plotting all the xy ordered pairs for a pair of variables, one of which we called explanatory, one of which we called response. And so we're going to go back and look at scatter plots through the command xyplot and try to say some more, learn about some more things we can say about scatter plots and our analysis thereof. And so we're going to be looking at the data set Rail Trail, and it's in a package which you may not have loaded yet. And so what I'd like you to do, if you're following along with this, is go to your Packages tab and make sure that the package Mosaic Data is the check mark is there, and because our data set is going to live inside that one. So it may take a minute to install some things for you when you check that box, but we want to add this to it. And I'll just point out that inside here is the data set Rail Trail. And we can learn a little bit about what's going on here using the help command. You'll want to enter data, parentheses, Rail Trail, view, remember with a capital V, Rail Trail, and then help Rail Trail to bring up this file. And I've got the data set over here. We're going to be looking at a couple of variables from this data set. We're going to be looking at the volume column and the high temperature column. And so just a real quick view over here at the help file. High temp is the daily high temperature in degrees Fahrenheit. Volume is the estimated number of trail users on a particular day. So what we're measuring is how many people were in a Rails to Trails area at a particular spot in Massachusetts. And we're trying to look at, for a given day, our individuals that are under study are days under which the park was open. And we're measuring the high temperature from that day and also the number of people that visited the Rails to Trails that day. So we have two numbers that are associated with the individual days in this data set. And so we can use xyplot to plot this. Remember, we want to choose one of these to be explanatory, one of these to be response. And if you recall way back from Chapter 1, xyplot, the response variable is the one that gets listed first. So I'm claiming that volume is response and high temperature is explanatory. So I'm going to give you just a few seconds. You might want to pause here to think about why we chose that. So hopefully you're thinking, well, people watch the weather, they see what the weather's going to be like, and one thing about the day is what the day's high temperature is going to be, and people will choose in response to the weather on a given day to decide whether to attend, to go to this Rails to Trails area. And so we're thinking that the number of people that are present there will be occurring in response to the temperature. So we're going to make the temperature, high temp, the explanatory variable, and the volume, the traffic that visits this park, is going to be the response. And just one other note, I'm going to add PCH equals 19 as an option to the XY plot. What that does is it makes our plot points closed circles rather than open circles. And so here is the result when we use PCH equals 19. And again, explanatory variable goes on the horizontal axis, response variable goes on the vertical axis. So what do we see? Well, I'm hoping that we see a slight upward trend, somewhat of an upward trend as we read left to right. So in general, apparently as temperature goes up, traffic and the rails to trails goes up as well. And so recall back in chapter 1, we were looking for whether we had positive or negative association. Here we would say that we've got positive association, moderately strong. It's not, the points don't fall along a line particularly closely, but we do have at least probably a moderate linear association between the number of visitors and the daily high temperature. So that's the sort of thing that once we generate a scatter plot, we want to be able to try to make a judgment. A, is there some sort of association? And B, does it seem to be linear? And so here are some examples of scatter plots. This would be a negative linear association between the two variables x and y. As x gets bigger, y gets smaller. Here's one that there's a pattern. There's definitely some sort of relationship between x and y, but it's not linear. We would call this curved or curvilinear. And so definitely a pattern, but this is not the sort of thing that we're going to be studying in this chapter. And this one looks somewhat linear. It trends downward as we read left to right, but then I would say that it definitely curves off as we get closer and closer. And so this is a scatter plot involving temperature, average temperature outside during a month, and that month's gas bills. I think we studied this, we looked at this one a little bit back in chapter 1 even. And we would say that there's definitely a negative association here, but it's not linear in the sense that the higher the temperature, the gas usage, the amount of money that you have to pay for the gas bill definitely is going down at a slower and slower rate the higher the temperature goes. And basically it's getting pretty close to zero. So definitely a relationship, but not linear. And then we could have just a cloud of points. There's really no relationship at all here, curved or linear or otherwise. And so as we move, as we say here, as we move to the right, the cloud neither rises a little bit or falls a little bit, just kind of hangs there. So we can generate scatter plots. We want to be able to describe what we see, but we are going to be focusing on those where there's some sort of linear association, be it positive or negative. And so suppose we look at a scatter plot and we decide that there is some sort of linear association between the two variables. We'd like to talk about how strong is that association. So we're going to come up with a numerical measure for the strength of linear association. We're going to call it correlation. If you go to page 310 in your text, you'll see there's a formula at the bottom of the page, but we're not going to try to use that formula. We're going to let R do the work for us, RStudio. So initially, here's the command that I'm going to use. It's called a with command, and we give it the data set, rail trail, and then core is the command that computes the correlation between two variables. So I give the two variables I want to find the correlation for, and then I tack on this option use equals complete.obs. And so what this does is it doesn't, core won't work all the time if there's missing data. And so this tells core just to look at those values for which we have both values of volume and high temperature. And we see that the correlation turns out to be 0.583 to 3 decimal places if I round to 3 decimal places. And so let's talk a little bit about what are some of the properties of correlation. So what does a number like 0.583 mean? So R, we're going to use a lowercase r to stand for correlation. And so here are some properties that R has. It's always going to be between -1 and 1. And so the largest R correlation can be is 1, and that's going to occur when all the points would lie on a line that has a positive slope. R equals -1 can occur only when all the points lie on a line with negative slope. Invariably, we're going to have numbers between -1 and 1. Positive values of R indicate positive association, negative values indicate negative association. That's good. But strength is measured by how close R is to the edges of this interval from -1 to 1. So when R is closer to 0, that's an indication of weak association. And when it's close to -1, that's the stronger negative association it's got. And if it's closer to 1, the stronger the positive association that it has. Our example where R was 0.5826 to 4 decimal places, that's moderate, almost to weak, but that's a moderative positive association. So it's not particularly close to 1. So here are some other examples of scatter plots along with the associated correlations. Here's a case where all the points almost lie on a line with positive slope. And so you'd expect the correlation to be close to 1, and it's very, very close to 1, about 0.99. Here's one that's pretty similar to the case that we're looking at. It's positive. We definitely see an upward trend. It's not especially strong at all. This is moderate to weak, I would say, and the correlation was 0.526. A relatively strong negative association here. This is about negative 0.92. And a weaker negative association, not very strong at all, but we can make sense of a downward trend, a general downward trend to the points. But there's so much scatter here, we don't expect the correlation to be very, very close to -1, and it's in fact about -0.3. And here's a case where we would see no upward or downward trend, and so we would expect the correlation to be very close to 0, and it is. Apparently, it's very slightly positive. Okay, so we have this number that we can attach to scatter plots when we see evidence of linear association. And now let's think about the question, well, what would be a good line to use to describe this association? If I had to come up with a line that best described the linear association I see, how would I come up with the equation for that? We're going to use an RStudio command ultimately, but first I want to show you how we can come up with an approximation for this. And so we need to remember a little bit about how we find the equation of a line. One way we can find the equation of a line is if we know the slope of the line and a single point that lives on the line. Then we can use what we call the point slope form of the line. If x0, y0 is a point on the line and m is its slope, then the equation of the line is going to be y minus y0 equals m times x minus x0. I imagine you've seen this before. So this is meant to be review about the form of the equation of a line. So what we need to do is we need to figure out how we can come up with an approximate slope for the line which, quote, best describes the association we see. And we also need to know something about a point that would live on that line. And it's going to turn out that there are 5 numbers that we need in order to do this. We need the means of the 2 variables that we're interested in, the standard deviations of the 2 variables that we're interested in, and the correlation. So if we know x bar, y bar, sx, sy, those are our standard deviations, and r, we're going to be able to come up with the equation of the line. Here we are. This is what we do. So the slope is going to be the standard deviation of the y values, the response values, divided by the standard deviation of the x, the explanatory variable, the standard deviation of the explanatory variable, times the correlation. So it's the ratio of the standard deviation of response to standard deviation of explanatory times correlation. And then the point x bar comma y bar, mean of the explanatory values, mean of the response values, that's going to be a point that lives on the line. So using our point slope form, we get the equation y hat equals y bar plus the slope sy over sx times r times x minus x bar. So you might ask, why am I using y hat here instead of y? And so I'm using a different symbol other than y because I don't want to get confused. Y is going to stand for actual response values, and y hat is going to stand for points that are on this line of best fit. And so we're going to think about them as response values that are predicted by the linear formula that we're coming up with, not the actual values. So that's why we're using a different symbol, and it's conventional to use the y hat. So let's do that for our rail trail example. Remember, we use favstats to get means and standard deviations. So I'm going to be focusing on the means and standard deviations of the temperatures and the mean and standard deviations of the volumes. So it looks like on average, about 69 degrees was our high temperature with a standard deviation of 13 degrees over the period that was examined. The average traffic in a day was about 375 with a standard deviation of about 125, 7.5. So we're going to keep these numbers. We have the correlation already computed. And so I've got my means, my standard deviations, and the correlation. So the slope is going to be the standard deviation of the y's divided by the standard deviation of the x's times the correlation, which is about 5.7. And then y hat, I've written it slightly differently from what I had before. I've moved the y bar over to the other side. If I written y hat minus y bar equals slope times x minus x bar, and then if I just add y bar to both sides, this is what I would get. So I get y hat equals 375.4 plus the slope 5.703 times x minus the x bar, the mean. And if I distribute, do a little bit of algebra, distribute, collect the constants together, I get the what we might consider the what we call the slope intercept form. Y hat equals negative 17.14 plus 5.703 times x. So I'm keeping 4 significant digits. I'm not keeping a consistent number of decimal places. I'm keeping 4 significant digits consistently here through in this part of the calculation. So that's our approximate line of best fit that describes the relationship between high temperature and volume. So one of the things that we want to get a little practice on is interpreting the slope of the line. So let's remind ourselves a little bit about slope. We think about slope as rise over run. I can think about it as change in y over change in x. And the units on slope are always going to be the units of the response per unit explanatory. Okay, so let's think about it. The units on the response are people. The units on the explanatory are degrees Fahrenheit. And so what we're saying is for every single time I increase the temperature by 1 degree, so for every 1 degree increase in high temperature, the slope is going to be the increase in the number of visitors. And so since our slope is about 5.7, that means for every 1 degree increase in high temperature, the number of visitors on the rails to trails will go up by about 5.7 people. That's what the line predicts. So I can think about this 5.7 as 5.7 over 1. So for when I rise temperature by 1, I raise people by 5.7. Here's a picture of this approximate line, and it does seem to run through the center of the data reasonably well. So this is looks, at least for to our eyes, to our eyeball, for an eyeball estimate, a pretty decent representation of what a single line might be to try to represent the relationship between these two variables. So at this point, I want you to stop and do a little bit of practice. There's a data set in the Tiger Stats or Tiger Data folder. It'll be already loaded for you. So if you just do data stumps, view stumps, remember view with a capital V, and help stumps, you'll see information about what's going on with this data set. So I'm asking you to do that. Then I want you to figure out which one should be your explanatory based on the description you see of the data set, which variable, stumps or larva, should be explanatory, which one should be response. Make a scatter plot once you've made those choices. Describe the linear relationship that you see, or if it's linear or not. And then use favestats to get the means and standard deviations. Use the with command with core to find the correlation. And then find the approximation formula using the formula that we saw earlier. And then write a sentence that interprets the slope that you found. So I've got some answers on the next 2 or 3 slides here, at least partial answers, to help you check your work. But I would encourage you to stop at this point and try to do this work yourself. So why don't you pause the video, look and see what you can come up with on these, and then when you're ready to move on, start the video again, stop the slideshow at this point, and just do the work, and then you can check your work after you've tried them a little bit. So I'm going to go on now and briefly go through the output that I've generated for you just for checking your work. So this is the scatter plot that you should get. apparently we want to choose stumps as our explanatory variable. We see that there is a positive linear association here of some sort. And so if you do favstats, you'll get these values for the means and standard deviations. If you do the with core command, you'll find that this number down here is the correlation. And this would be the approximate value of the slope, and this would be the equation of the line. And so this would be my interpretation of the slope of that line. So hopefully you stopped and tried these out yourself. You can verify that this is indeed what we should get. If you have questions, I'm happy to answer them when we get together in class. Okay, so a couple more things we want to do here. One, I want to give you the command that we're going to use in our studio to find not just the approximation to the best fit line, but actually find the best fit line. And so it's a command called LMGC. It looks like an I up here, but that's really a lowercase l. LMGC. It stands for Linear Model, Georgetown College. And we don't have to give it too much. We give it our two variables. Again, it's going to be response tilde explanatory. We tell it what the data set is, and then we use graph equals true. So let me go ahead and enter this into our studio for us. And we'll see that we do get a lot of output here. And so we get some information about the correlation. We get the regression equation, some other information that we're going to talk about before too long. And then we get a plot with the actual regression line present in the scatter plot. So let's go ahead and take a tour of this output. Correlation matches what we had before, 0.5826 to 4 decimal places. And the approximate regression line we came up with is actually pretty close to the real thing. It's negative 17.08 to 2 decimal places. And this is not far off at all. This 5.702 if we rounded versus 5.703. So we came up very, very close. We won't always do quite so well as we did with this one. But the actual line of best fit is called the regression line. And so we found the equation of the regression line here. And so our approximation did very well, better than sometimes in this particular case. And then we will talk about R squared in a few slides. Standard error will come up in the next video/slideshow. And then this is a slightly different looking scatter plot, but again, we see the regression line running through the plot. Looks very similar to the one we saw earlier. So LMGC is our friend, and we want to be able to use the output of LMGC to do some things. So once we've got the actual regression equation, what are some things that we can do? Before we tackle some problem solving, let's mention that a lot of times the regression line is also called the least squares line. And what does the term least squares refer to? Well, let me go back to our plot here. What we're doing is we're finding the single line that minimizes the sum of the squares of the vertical distances from the points in our scatter plot to the line. So what I could do is I could draw a line segment that joins this point, drop a vertical line from this point to the line. I could do the same for this one. I could do for this one here. I could do these points down here. I could draw all these vertical line segments. And so what the least squares line is, what is the single line that minimizes, as I said, the sum of the squares of those vertical distances. You can use calculus to find this. We're not going to try to do that in this course, but it basically is a calculus problem, something that you could see in say, a Calculus 2 or Calculus 3 course. But what it does is it's, as I said, minimizing the sum of the squares of these vertical distances. So I'd like you to run LMGC on the stumps data and see how the output that you get from it in terms of correlation and the regression line, it compares to what our approximation was. We will do this in class, but I want you to try it yourself too here. Now, here are a couple things that we can do with the regression equation once we've got it. One thing is we can use it to predict things. So if I've got a new explanatory data point, I can pop it into the regression equation and I can come up with a predicted response value. So for instance, if I knew that the predicted temperature for the day ahead is going to be 70 degrees Fahrenheit, it's a nice, spring day or mid-fall day, we can use the regression equation to predict how many people we think will show up at Rails to Trails that day. So we would just put it into our equation, negative 17.14 plus 5.703 times 70, and we get 382 people. So we predict 382 people to show up that day. Question for you, what would be the predicted number of clusters of beetle larvae on a plot that has 4 stumps? So hopefully you've run LMGC to get the regression equation, and so you can use that regression line to predict the number of beetle larvae. Another thing that we can do besides doing prediction is to find the difference between what was predicted for a data point that's in our data set and the actual response. So residual is the difference between an observed response and that which would be predicted by the regression equation for that data point that's in our data set already. So if xi comma yi is the data point and yi hat is the predicted response, the residual is the difference between the observed minus the predicted, y sub I minus y sub I hat. So again, observed minus predicted. The order of subtraction matters. So if I wanted to use the regression line in a Rails trail data set, looking at the day that's in line 10. So if I go down to line 10, the high temperature that day was 79. So if I go to 79 degrees, the volume is 547. Let's double check that. So 79, volume 547. And so we pop 79 into our regression equation. We get a predicted value of 433.4 people. So the residual is the actual observed 547 minus 433.4, which is 113.6 people. So that day, there were over 113 more people than would be predicted by the regression equation. Just a note here, positive residual indicates the point lies above the regression line. Negative residual would indicate that the point lies below the regression line. Let's see if we can find this point on our scatter plot. So I'm going to go back here. Temperature is 79, so we're over here. 479 looks like it's probably this number right here. And so we're probably looking at this point that's 113, 547, sorry, that's probably this one right here. So we're talking about a difference of about 113 between the point on the regression line and the point in the scatter plot. Positive residual lies above the regression line. Negative residual lies below. So I'll ask you for practice. We'll talk about this in class. Look at the day represented by line 39 in our data set. Can you find the residual for day 39? One little bit of warning here. Regression line is meant only to describe the nature of the relationship between the explanatory and response over the range of explanatory values that you see in your data set. And so we wouldn't want to use this line to predict volume on days whose temperature was outside the range of the temperatures that are in the data set, which is approximately 40 degrees to 100 degrees. And since our stump data only went between plots that had between 1 and 5 stumps in them, we wouldn't want to use the regression equation to try to predict how many clusters of beetle larvae there would be on a plot that has more than 5 stumps. So this is called extrapolation, trying to use explanatory values outside the range of the values in your data set for prediction purposes. We don't want to do that. One last thing before I turn you loose on another example to try. R squared literally is the square of the correlation. So it's going to always be a positive number. And what we want to understand is that R squared gives us the percentage of variation in the response variable that is attributable to a linear relationship with the explanatory variable. Because the points don't all lie on a line, it's clear that there are other factors that are involved in explanatory power between the explanatory and the response variables. And so R squared tells us what fraction of variation in response can be directly is directly related to the linear relationship it has with the explanatory variable. R squared for this should say rails to trails example. My apologies for that. In the rails to trails examples, about 34% of the variation in daily traffic is explained between linear relationship between high temperature and volume. I'd like you to go back and look at the output to LMGC for the stumps example and try to write a corresponding sentence for the value of R squared in that case. We will talk about that in class. And then finally, another problem for you to work on in advance of our getting together is to look at the variables weight and systolic in the NHANES 18 data set and do all the work that we've done here in terms of getting a scatter plot, finding correlation, using our formulas for estimating the regression equation, then using LMGC to find the actual regression equation and writing sentences that interpret the slope and the value of R squared. And we can maybe play around with prediction and residuals when we get together too. So that's it for this. There's plenty for you to try. Hopefully you can get comfortable with this work using XY plot, using phase stats, using core, using LMGC to help us answer these questions.